Good morning, folks. We're a little thin, but as people filter in, I'm going to get started. So, all right. So just a heads up, a reminder that the exam is on Monday, which is the last day of class. The next exam. After class today, I'll be posting some study guide and some practice questions. I will also be posting a video of a case study for you to practice some net ionic equation stuff, which is what we're going to talk about at the beginning of class today. But what we're going to do is we're going to start with kind of recapping what we talked about last time, which was different types of chemical reactions. Okay, and the last type that we talked about was double displacement reactions, where we have different classes of those. But so in a double displacement reaction, okay, we have two things that are exchanging, right? So we've got the here we have both A and B swapping partners. So those can be precipitation reactions, which is what we're going to talk about with net ionic equations later today. Acid-base neutralization, which we'll get to by the end of class today. Okay, and those that where the product of your double displacement is something that decomposes into a gas that's going to float out of solution. And our last example of double displacement is something called a ping pong enzyme mechanism. So I went through it quickly at the end of last class, and we'll go through it in more detail now. Okay, so the example that's here is an example of a reaction that plays an important role in the human body. Okay, so this is this reaction here is an enzyme catalyzed reaction. So what that means, an enzyme is a protein that catalyzes or makes a reaction go faster. Okay. So in general, it controls the rate of a reaction. Okay. And in this case, the reaction that it's controlling is the transfer of, this is called an amino group. And it's transferring the amino group from a molecule called aspartate, so that's what this molecule is right here, to a molecule called alpha-ketoglutarate, which is the molecule labeled number 2 there. Okay, and again, these are two molecules that look very similar. They differ by 1 carbon. Okay, the enzyme in this case is called aspartate aminotransferase. So if you study, biology or biochemistry, and you study enzymes, or if you have studied enzymes, you'll know that they're typically named by the reaction that they catalyze, that they help go faster. And so this is again telling you that this enzyme helps transfer an amino group from aspartate. Okay. And so in this case, okay, we have a swapping of two groups, right? So that's called an amino group right there, and then this group right here is called a carbonyl. So these are just names that for chemical kind of features, chemical groups that we use in organic chemistry. So we're swapping the amino from the carbonyl. We're using this protein to help these two reactants form this product. Now, where the ping pong in the name comes into play is not in the what reaction is happening, but the how the reaction happens, okay? So when you see something, an enzyme that has a ping pong mechanism, what that means is that the reactants don't bind or stick to the enzyme at the same time, okay? So the ping pong means the two reactants, and I'll use the word stick, but what we typically use in chemistry is the word bind, okay, to the enzyme at the same time. They bounce, if you will, like a ping pong ball, on and off. And so the way this works in this particular reaction mechanism, okay, is that molecule 1 here, the aspartate, is going to bind to the enzyme first, and this group does not get transferred to the other reactant right away. It actually gets transferred to the enzyme. The enzyme holds on to that group, okay? And this product, the first product, pops off of the enzyme, okay? Then the alpha-ketoglutarate binds to the enzyme, and the enzyme gives it the amino group that it took from the first reactant, okay? And then once that has been transferred, then that product, which is called glutamate, okay, comes off of the enzyme, okay? And so this molecule right here, these are normal products of metabolism, okay? And so if you have a blood panel and you're looking for liver function, okay, the enzyme, the protein that helps this reaction happen, okay, is one of the things that we test for when we do a blood panel and we're looking at liver enzyme function, okay? So if the levels of this are too low or too high, you know there's some type of malfunctioning in the liver, okay? Also, just a quick note. This is a molecule called glutamate, okay? If you've ever heard MSG, monosodium glutamate, okay? Basically what that is it's an ionic compound made of this molecule that's a normal product of normal metabolism that has a positive sodium ion, you know, neutralizing one of those negative charges, okay? So that's what that is. All right, so we've gone over different types of reactions. So now what we're going to do is we're going to talk about when we have molecules in solution. Okay, so we're going to talk about aqueous solutions. Okay? And when we're talking about something in aqueous solution, okay, we're going to be using some typical terms that one uses when talking about solid compounds that we then mix with water and what that means and what happens. So this picture that's up here is just showing you actually molecules that are insoluble precipitating when you get a chemical reaction occurring in the liquid. All right, so aqueous solutions, okay, what are they? We use a few terms that we'll define here. Solutes, okay, so this is going to be a solid chemical, okay, that mixes, okay, with a solvent, okay. In this case, the solvent is water. So a solvent, okay, in general so this is when we mix, we're going to form a homogeneous mixture. And a solvent is a liquid that is used to dissolve a solute. All right, and so we categorize aqueous solutions by the nature of what's dissolved. So, but when I'm talking about something dissolving, okay, so I'm going to draw a pretty horrible beaker here, but it's not too bad. All right, and I'm going to make a, all right. Okay, so I have a beaker. In my beaker are molecules of water, which I'm going to just show as little, we know water is an angled molecule, right? So this is what we would call pure solvent. It's just a liquid that has one molecule making it up, okay? Now, if we can have solvents where we mix two liquids. So if you do something like drink a, well, let's talk about something that just has, like 2 molecules in it, okay? Let's say you are going to have a shot of vodka, which no one in this room would ever do, I'm sure. At least not before 9 a.m. in the morning when you have chemistry class, I hope. So vodka is a mixture of 2 solvents, ethanol, okay, the molecule ethanol, and water. Okay, so you can have 2 liquids that mix, okay? They're both considered solvents. But in the case of the aqueous solutions that we are talking about, okay, we are going to have a pure solvent where we only have 1 molecule type, okay? So we could have a mixed solvent where we have 2 liquids that mix together. All right, so what happens, and I'm going to draw a third beaker here. Okay. So we could have a molecule, okay, that is going to mix well with our solvent, okay? And what happens is I will have my water molecules, okay? So let's say I'm making Kool-Aid, right? And I have sugar in that Kool-Aid, right? And so the sugar is going to do what we call dissolve in the solvent, the water. Okay, so let's call this a sugar molecule. And when I put that in, if something dissolves, what it means is that the molecules in my solid, so let's say I take solid sugar, right, are going to kind of separate from one another and become completely surrounded, okay, by what we call hydration shells in the solvent. So in this case, okay, this is a solute, okay, so this is the solute, the sugar, okay, dissolved in the water. Okay, so what you see is each individual molecule is surrounded by waters and they're not in direct contact with one another anymore. Okay. Oh, I erased my beaker, didn't I? All right, well, let's see if we can paste it. There it is, it's back, yay. Okay, so the other thing that we can have is I can have my molecules, right, of water. And I can try putting in a solid that does not mix well with the water, okay? And so in this case, okay, I have what we call an insoluble compound. So this is one that won't mix with water. And so we're talking aqueous solutions here, but I could have something like oil could be a solvent for something that's nonpolar, okay? And so if I took sugar and tried to dissolve it in oil or salt, it wouldn't dissolve, it would be insoluble. Okay, and so what happens when we try to put something that's insoluble into our solvent is that it's just gonna stay clumped together in its own little corner of, the bottom of the beaker, okay? And when we have chemical reactions, okay, that produce an insoluble compound, then what you see happening is you see that process of, well, crashing out of solution, we call it, or precipitation occurring, okay? So the solute is insoluble in water, okay? All right, so the other thing that I had mentioned, right, is I use this term homogeneous. When you have something that is soluble, that is very, well soluble in your solvent, so it will dissolve well in water in this case, okay? It will make a homogeneous mixture, which means that it's uniform throughout. So homogeneous means that it's uniform throughout. So let's say I go down to the latte lounge and I get some tea, and one of the things that they have there that you can use, especially if you get like I like to get iced green tea there. And they have something called simple syrup where they have all the sugar and everything. And what simple syrup is it's just a concentrated solution of sugar in water. Okay, so just like this. And it's good for iced tea because you can put a little squirt of this pre-dissolved sugar and it will mix quickly into your iced tea. Whereas if you tried to put a packet of solid sugar in, it would take a while to dissolve in your cold tea. Okay, so but if I took that simple syrup, okay, and let's say I took 5 milliliters of that, okay, and that's a tablespoon, okay? And I measured how many sugar molecules were in there. And then, Noah came along and he took the next 5 mils and measured how many sugar molecules were in there. There would be the exact same number of molecules because every spoon or every 5 milliliters, every, amount of sugar that I take has the same exact composition. Okay, in that solution. So that's what it means by homogeneous. A heterogeneous mixtures, an example would be something where, you've got a lot of molecules down here and like a couple up here. This is not how things that are soluble in aqueous solution behave, right? Where, you've got a little more in this unit of volume down here than you do up here, okay? So that's what we mean by homogeneous, okay? Okay, so another term that we can use when we're talking about things dissolved in water, okay, is we can use the term electrolytes, okay? And electrolytes are what you get when you have ionic solutes dissolved in the solvent water, so that what happens is, okay, so here the process, so this figure shows kind of the process of dissolution, okay? Because if you'll notice, it is not showing a homogeneous thing right now, right? So what this is sodium chloride in water, okay? And so the chloride ions are shown in green, the sodium ions are shown in gray, and then the water molecule is shown as a red oxygen with 2 white hydrogen atoms, okay? And so what you'll see is, this is what the salt crystal looks like when we start to put it in the water. And then as it dissolves, what you see is the ions get surrounded by water molecules and they separate, okay? And so to get back to our theme of, positive and negative charges and the way they interact, controlling a lot of chemistry, okay, well, I want you to look kind of closely at the way the waters are arranged, okay, around the chloride ion versus the sodium ion, okay? What do you notice about the way the waters arrange around the chloride ion? Or how it differs from the way it's around the sodium? Yeah?
The hydrogens are pointed the in and the oxygen are pointed.
Right. So around the chlorine, okay, the hydrogens, these guys right here, okay, are pointing towards the chloride. And with the sodium, it's the oxygens. Now, if we think about what we know about bonding and electronegativities and polarity and molecular polarity, okay, one of the reasons that we studied that was to understand how materials behave. And if you remember, oxygen is much more electronegative than the hydrogens. So these bonds are going to be polarized, right? And there we have these little bond dipoles, right? Pointing towards the oxygen. So the oxygen is going to have that partial negative charge, and the hydrogens are going to have partial positive charges. And so this is, first of all, one of the reasons why ionic compounds are going to dissolve in water, a lot of them, okay? Because the water molecule acts like it has positive and negative charges, even though it's not, +1, -1, it's significantly polar, okay? And so you can have these favorable charge interactions between the kind of positive end of the molecule and the negative, the anion in our ionic solute. And then the cation is going to have favorable interactions with the oxygen, the negative end of the water molecule. Okay? So that's, one of the reasons why we get things dissolving in aqueous solution. Okay? So let's talk now for a second about why we call them electrolytes. Okay? So we call them electrolytes because when they are dissolved in water, okay, they can help conduct electricity. Okay? So conduct electricity when dissolved in water. So can anybody here tell me what electricity is? What do you know about what electricity is? If you took a physics class in high school or even physical science, you may have heard it described to you as a movement of electrical charge. And whether you're a chemist or a physicist, you will think of it as moving electrons, or you'll think of it from the proton perspective. But electricity, okay, is movement of electric charge. Through a material, okay? So think of it as moving electrons, okay? So when you have a copper wire, okay, remember how we talked about metallic bonding and how electrons would be kind of shared through material? Well, one of the reasons metals are so good at conducting electricity is because electricity is like pushing electrons through a material, okay? And those materials that are good at, distributing electrons throughout the solid are good conductors of electricity. When we think of pure water, okay, pure water is actually not really good at conducting electricity. Okay, so despite the fact that if you buy a hair dryer, it's got all these dire warnings about don't use this near water, which you absolutely should not dunk your hair dryer in water. Okay, but the reason that that's going to be a problem is because the water that comes out of our tap is not pure water. It's not like the distilled water tap in the lab where we have just water molecules. It's got all sorts of salts dissolved in it. So it has ions like this that can help move, actual charges, move electrons through the solution. And especially like if you're in the bathtub and you put bath salts in, now you've made it a solution that's really good at conducting electricity. Okay, so electrolytes, are going to be solutes. Okay, that when they dissolve in water, can help it conduct electricity. So, if you're thinking about your Gatorade, or your sports drink that says it has, electrolytes dissolved in it, okay? Or you can even get like Smart Water or some of the waters that are supposed, we don't have the sugar, but we have the electrolytes. Well, the electrolytes are those mineral compounds, those ionic compounds that, your body needs to convert, you need some of those metals to convert, sugar that's in your bloodstream into ATP, into energy that's going to help your muscles move, okay? So, so the electrolytes in your sports drink are the ionic compounds, the salts, not the sugar part, right? Because if we put sugar in water, it's not going to make it any better at conducting electricity, so we don't call it an electrolyte, okay? All right. So whether we're talking acids, bases, or electrolytes, okay, we're going to be using terms called strong and weak, okay? And so whenever I use the word strong, when I'm referring to a chemical phenomenon, it means that thing happens completely, okay? So strong, whatever it is, it means the process goes to completion. So we will talk about all the way. So we'll talk about acids being molecules that lose protons. And strong acids, every molecule that I put in solution is going to lose a proton, where a weak acid would be maybe only half of the molecules lost a proton, okay? So strong electrolytes are where for every molecule that I put in solution, okay? So every salt molecule here is going to completely break up into the sodium and the chloride ions, okay? So that's a strong electrolyte. I get the maximum amount of ions out of what I put into the solution, okay? All right, so the other thing that can happen, okay, is I can have something that is a weak electrolyte, okay? So this happens to be acetic acid, which is also an acid. So this is acetic acid. And when we say something, again, is weak, it means the process only goes all the way in a fraction of my molecules. So the thing that we need to clarify is there's a difference between, okay, dissolving and being an electrolyte, okay? So when I put my acetic acid into water, okay, every acetic acid molecule will be surrounded by water, but only some of them will have lost their proton, okay? So let's see if we can draw this out. So let's make CH3CO2. So I'm going to draw an assortment of my molecules, okay? Here we go. Okay, so if I have these molecules in my very short, squat beaker here, okay? what you'll see is that all of them are surrounded by water, so all of them are dissolved. But not all of them are what we call ionized, right? Not all of them have the negative charge. And I have neglected to put in the protons that got lost, so I'll add those now. So I have, 2 molecules that are ionized? So there'll be 1 proton here and 1 proton here floating in solution, okay? So in the case of acetic acid, okay, all acetic acid molecules are dissolved. But only, and in this example, 2 are ionized. And again, this is the ionized form because it is an ion now of acetic acid. Okay. So, something that's really important to keep straight, again, is being dissolved versus an electrolyte being ionized. Okay? And so if I had this same situation with my previous example, which was sodium chloride, which is a strong electrolyte, okay, what I would find is every single one of my sodiums would be ionized, and every single one of my chloride ions would be. So they would be completely broken up into the 2 ions. Okay. All right, so the same thing happens with HF, which hydrofluoric acid, which is has a reputation of being a very nasty chemical, and it is. If you've the only scene of Breaking Bad that I've ever seen is the one where he uses HF to dissolve the body in a bathtub, and it eats through the bathtub and falls through the floor of the whatever house or apartment or whatever it was. So it's a very nasty caustic chemical, but it's not actually a strong electrolyte. Okay, it is so not every molecule of HF that goes into solution is going to break up into a proton and a fluoride ion. Okay. All right. So, a non-electrolyte, okay, non means that it just doesn't happen. So it doesn't ionize, okay? So a non-electrolyte can still dissolve, right? So anybody know what this molecule is here? We've seen it before. It's methanol, okay? This is also known as wood alcohol. Okay, so methanol, okay, it is, very water soluble. So that means it will dissolve. But it does not ionize. So it is not an electrolyte. So when we put this into our beaker, okay, every single molecule is going to remain CH3OH. They are going to be surrounded by water, okay, surrounded by our little water molecules. And the water molecules will orient themselves, around the OH that's in here. I'm not drawing them in any particular orientation because I'm just trying to make the figure quickly. Okay. All right, so that is what a non-electrolyte would look like in solution. Okay. All right, so if we compare, again, the properties of these molecules, okay, strong electrolytes are going to conduct electricity well. Weak electrolytes are going to conduct electricity poorly, and non-electrolytes are going to not conduct electricity. And it's all related to the number of charged particles that you get when you put one of these molecules into solution. So strong electrolytes You get lots of charged particles in your solution. When you have a weak electrolyte, you get some charged particles. And when you have a non-electrolyte, you get no charged particles. Oops. In your solution. And so that's directly related to its ability to conduct electricity. Okay? So the things that we think of as strong electrolytes, okay, are going to be soluble ionic compounds, and we'll find out in a minute that not every ionic compound will dissolve in water, okay? And things that we consider strong acids, okay? And we'll talk about what acids are in a little bit. All right, and then weak electrolytes, okay, are going to be weak acids, and also the weak base, which is ammonia. Okay, so this is the molecule ammonia. Oops. I do that all the time. And then non-electrolytes are covalent compounds, things like sugar. Let's see, what's a good alkane that you guys might have heard of? Isopropanol, so rubbing alcohol, things like that, ethanol, alcohol, okay? All right. All right, so we can combine the notion of electrolytes and our reaction types, okay, to do things like make cleaner fuels. So you may have heard about, hydrogen fuel being talked about as sort of a green technology. But how do you get hydrogen? Okay, one of the major ways that people are trying to do this is trying to do it by breaking apart water, right? Into, oops, let's see. There we go. Nope, never mind. There we go. Okay. All right, that's not balanced. I'm not going to worry about it. All right, so hydrogen fuel can be, a good portable source of energy for a combustion engine. Okay, and so how would we get it? Okay, the way we can do this is we have to put electricity in. And so the way we can do that, okay, would have to involve controlling the reaction somewhat in what we call a fuel cell, right? A hydrogen fuel cell. Okay. And so you can have different types of electrolytes. Okay, so you can have polymeric materials. So if you want to think about what a polymer is, there's lots of different kinds of polymer. The wood, that's in a pencil or in a tree is a carbohydrate polymer. The plastic that the seats are made of. So polymers are these, big long chains of molecules, and you can make ones, okay, that are electrolytes, and that would be an electrolyte that exists on a membrane. So your electrolyte, okay, is actually, in this case, is a solid polymer material. All right, and then water, okay, is going to react over here at what we call the anode, okay, and that's going to form our oxygen, and it's going to form the hydrogen, okay, and those hydrogen ions, or the hydrogen molecules, are going to be ionized. Okay, and what will happen is you'll get electrons flowing through a circuit, and eventually you're going to be getting hydrogen gas out of it, okay? But to do this process, you have to have a material, okay? And so the electrolyte is this gray stuff that's in there. And so that's what your materials, your charges are going to be flowing through. All right. All right, so now we're going to talk about the solubility of ionic compounds. So the back of the periodic table, okay, has kind of the roadmap. So the periodic table that I gave out earlier in the course, and there's more up here on the lectern that you can take, has what's known as a solubility table on it, okay? So the basic idea is if I have an ionic compound where I have a metal here represented by M, that's metal cation, and then I have my anion, which is shown here as X, okay? When I put it into water, okay, is it going to do this, break up, and then have the water surrounding it? Or is it going to do this? And it stays associated with itself, and the water just kind of avoids it. Okay? So, if it dissolves, it's soluble. If it doesn't dissolve, okay, it's insoluble. So, how soluble is soluble? Well, not every compound, even when it is, you can dissolve it in water, not every compound has an infinite solubility. So every material that will dissolve in water has a maximum amount that you can get dissolved into water, okay? So every soluble compound has a maximum amount that can be dissolved in a given amount of water, okay? And so we typically express these in grams of solute per 100 grams of water, okay? So something that is more soluble, okay, is going to have a higher number of grams, can go into 100 grams of water, can dissolve. And so what happens when you get, so let's say I have two compounds, and one, it has a solubility, what we call a solubility of 10.5 grams per 100 grams of water, versus something that where I can put 105 grams per 100 grams of water. Okay? What we would say is this compound is more soluble. Okay? Now, what do you think happens, okay, if I try to put 12 grams of, so we'll call these compounds A and B, okay? What happens if I try to dissolve 12 grams in water? What do you think is going to happen? So, can we all agree that the first 10.5 grams is going to dissolve and the molecules are going to separate and be the ions will be surrounded by water, okay? So what happens to that extra 1.5 grams? Well, that extra 1.5 grams is not going to dissolve, and it's just going to sink to the bottom of my solution, okay? So you can make what we call a saturated solution by putting kind of the maximum amount of stuff into the water, okay? And then sometimes if I heat up a solution, I can get more to dissolve, and if I cool it down slowly and not disturb it, I can get what we call a supersaturated solution, which is where I have more than can actually dissolve. And you can do this with a molecule called sodium acetate. So if you've ever seen those kind of reusable hot packs where you can, what happens is there's this liquid in it, and there's a little, usually a little metal disc that you can bend. And when you do that, okay, so the solution is supersaturated sodium acetate that's in there. You put a little, you click the little metal thing, and what that does is it disturbs the solution so that then that extra sodium acetate precipitates out of the solution, okay? And when it does that, it gives off heat. And so that's why these things can be used as heating packs. But then it becomes a solid. And so to regenerate that, you would put it in boiling water, and that the hot solution can then hold more of the sodium acetate in it. When it cools back to room temperature, it's a supersaturated solution. So, all right. So, how do we know whether, if something is soluble? Okay, so solubility is the degree to which something is soluble, okay? Or amount. All right, and then whether it is going to dissolve or not, okay, we use solubility tables. And you used this in lab when you did the net ionic equations lab, okay? So the way that we read these, okay, is there's kind of a top and a bottom to the table. Okay, the top of the table tells you things that are always soluble, okay? And then the column to the right are going to be the exceptions, okay? So if we look at the top of this table, okay, we can see that anything that's a compound with salt is going to be soluble. There are no exceptions, okay? Anything with potassium and anything with ammonium is going to be soluble, okay? So if we go down a little bit and we look at fluoride salts, okay, things that are combined with fluoride ion into an ionic compound, okay, you'll notice that, so for example, hydrogen fluoride is soluble, okay? But we have some exceptions. So if we have calcium, strontium, barium, or lead, okay, that is not going to be soluble. But if I take, let's say if I take rubidium. So rubidium, okay, it makes a +1 ion, okay? So rubidium fluoride is soluble, okay? All right, so that's what that ionic compound is. All right, so these are, again, the top is things that are generally soluble with a few notable exceptions. The bottom of the table, okay, are things that are generally insoluble, okay? So if your compound is a hydroxide or an oxide, so if the anion in your ionic compound is OH minus or O2 minus, okay? So for example, let's see, what can we make? Let's see. Let's say magnesium. So magnesium forms a +2 ion. Okay, so magnesium hydroxide, okay, is not soluble. That's how we would read this chart. But our exceptions are if we have sodium, potassium, and barium. Okay, so barium hydroxide is soluble. It will dissolve. Okay? All right. So, when we are combining chemicals that are in solution, okay, reactions can occur that change the solubility. Okay, so something we call net ionic equations is how we describe those processes. Okay, so, and precipitation reactions are reactions that occur where we have two soluble reactants, okay, and they form an insoluble product. Okay, and so the way we figure out what reaction happens, okay, and so the thing that you see is what you see, on this slide here, right? You see cloudiness forming in the solution. You see precipitation, something no longer being soluble. All right, so when we write chemical reactions, we put the state of our material in parentheses afterwards. So it can be solid, liquid, gas, or aqueous. And aqueous means dissolved in water. Okay, so this is dissolved in water. So if you see that after a chemical in your equation, then you know that that thing is going to break up into the two ions that make that. Okay, so we could write our all of our ions. So we've got our silver and we've got our nitrate. Okay, and we've got sodium and chloride. Okay, so in the case of again, when you mix these things together, if you see a precipitate, okay, then what you will see, what you're observing is that, we've got a reaction between the cation from one and the anion for another. So we have silver chloride and sodium nitrate, okay? And we have to figure out, at the end of this process, are we going to see, are we going to see some solid form, or is everything just going to stay as ions in solution? So we would go back to our table, okay, and we would look for chloride. All chloride things are soluble except silver chloride, okay? So that's one of our exceptions. So this thing would not be soluble, and it would form a solid. Okay, so this is an insoluble, what we call precipitate. Okay, and then we'd look and see sodium nitrate. So let's look for everything with sodium is soluble. Okay, so our sodium nitrate, all of our nitrate compounds are soluble, no exceptions. So this is going to be aqueous. And so what that means is what we actually have in solution, okay, is we've got silver chloride solid, and we have sodium and nitrate ions floating around in solution, okay? All right, so we are out of time for today. So I'm gonna not just post the case study, but just another 5 minutes on going through net ionic equations. And so what you should do is I'll send an email, watch the net ionic equation video, try to do the case study from what's on the slides, and then you can watch the video where I go through the answers to it, okay? All right, I'll see you on Friday.